Greetings. Just a little video to go with the problems 15 and 16 in this week's homework. So 4.5, hen eggs. The distribution of the number of eggs laid by a certain species of hen during their breeding period is 35 eggs with a standard deviation of 18.2. Excuse me for a frog there, not a hen. Suppose a group of researchers randomly samples 45 hens of these species, counts the number of eggs laid during the breeding period, and records the sample mean. To repeat this 1,000 times and build the distribution of the sample mean. So what is this distribution called? Okay, so let's do a little review from section 4.1, because that's really where this question is starting from. And what we know is that if we start off with the distribution of eggs laid, okay, so here is, we'll call this the distribution of X. And this is the distribution of how many eggs that each of these hens lay. And they say for a certain species of hen during the breeding period, there are 35 eggs with a standard deviation of 18.2, okay? So this distribution of eggs has a mean of 35 and a standard deviation equal to 18.2. So that suppose part, or that given to us piece, it tells us that this is the population of hens, okay? Now what our researchers did is they sample 45 hens of these species, count the number of eggs laid during the breeding period, and record the sample mean. Then they do that again 1,000 times. So in other words, what they do is they come into this distribution, and they grab out of this distribution 45 hens. And they take those 45 hens, and they feed them to the tool called X bar, all right? And what X bar spits back out, what it gives you is a sample mean. And so say the first time they do this, they get a sample mean of 32. Okay, so that's their first 45 hens, they get 32 eggs as the average number of eggs laid per hen during the breeding season. Then they sample again, and they do that again. And the next time they say they get 37. And so the first time was 32, then the next time is 37, and then they do it again, and then this time say they get 36, and they do it again, and this time they get exactly 35, and they do it again, and this time they get 31, etc., 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 and they do this 1,000 times. So down here, say the 1,000th time they do it, say they get 33 eggs, okay? So there are 1,000 X bars in here. So notice every one of these numbers in this column right here, these are all X bars. Now if we took and we created a histogram of these numbers, what we would see is that it would be bell-shaped. And it would be a little bit tighter in its distribution. If this is on the same scale as the previous one, of course I'm assuming that the distribution of eggs laid by the hens was normally distributed. That's not a horribly bad assumption, okay? But notice this is the distribution of X bars. Now what we would expect is we would expect that distribution to also be centered about the same mean as the population one. Because why? Well, every one of these numbers here, what their job was, what they were trying to do was estimate this number, the 35. So you've got 1,000 of these numbers here, each of these from a sample of 45, and you put them all into this histogram here, and they better dang well line up very close over the top of 35, which was the population mean, okay? Whereas the mu of the X bars should be equal to 35. Now, the mathematics behind how to calculate the standard error is a bit beyond this course, but the standard error of the mean, which is given by sigma sub X bar, that's equal to whatever the population standard deviation was divided by the square root of n. That's that standard error formula that we've been working on, okay? And so what that means is that this distribution right here would have the standard deviation of the X bars is going to be equal to 18.2 divided by the square root of 45. Now, it's not the square root of 1,000. That's how many of these means that we calculated, but every one of those was a sample of 45. In other words, this number right here, the 45 here, that's our n, okay? All right, now that was a lot more than was necessary to actually answer this question. This was just basically a memorization thing, but it's really important that you understand the fundamental idea here. This goes back to the last question on the reading quiz, which was basically getting around to this, that the standard error is going to be smaller than whatever the population standard deviation was, because it's divided by the square root of n, which is the sample size. So the larger the sample size is, the smaller the standard error is going to be. Okay, what would you expect the shape of this distribution? Be symmetric, right, skewed, etc. It's going to be symmetric. The central limit theorem, many times abbreviated as the CLT, that's the math behind how we get from here to here, says that if the random sample is greater than 30, then the sampling distribution is going to be nearly normal. It'll be approximately bell-shaped, okay? So calculate the variability of this distribution and state the appropriate term used to refer to this value. Okay, so let's go over to the calculator for that. Well, we've already written down what it is. We've got to actually go do the calculation now. So the standard error is going to be given by 18.2 divided by the square root of 45. If you're an old dog TI like mine, be sure and close off that square root with a parenthesis on the other side. Okay, hit an enter. And it's 2.713, etc., okay? So that's what the value of, we'll go ahead and just type it in here, okay? We can do that. Remind myself again, was it, how far they want us to go here? I don't know, we'll go out 4 places since they didn't tell us any better. So 2.7131, so 2.7131, okay? All right, cool beans. Okay, and so what was that referred to? What is that number? That is the standard error, right? So we would circle this bad boy right here, where you'd tag in the standard error for that one, okay? All right, so hopefully you're all feeling warm and fuzzy about that. I'm gonna erase my board here because I'm gonna need to slide down. So let's go ahead and get rid of all of this scribbles all over here. And let me scroll down a little bit. Okay, suppose the researcher's budget is reduced and now they're only able to collect the samples of 10 hens instead of 45 hens. The sample mean and number of eggs recorded, and repeat this 1,000 times. A new distribution of sample means is created. How will the variability of this new distribution compare to the variability of the original distribution? Okay, so what they mean by the original distribution here was n equal to 45. In other words, when they did the first one. And now what they have is that n for their new sample, n is equal to 10, okay? So over here we notice n was equal to 10. All right, so let's put all 3 of them on the same page here so we can see. So we're assuming that the original distribution was roughly bell-shaped. So this is the distribution of eggs. So that's the distribution of eggs. And what we know about that distribution is we're given that the mean was equal to 35 and the standard deviation was equal to 18.2. Okay, so the sampling distribution of x bar with n equal to 45, that's what we did in the previous problem. And what we saw was, as we think about it, we know that that's going to have a very sharp peak because as you make the standard deviation smaller, that means everybody is more packed around the mean because that's what the standard deviation measures. It measures the average distance away from the mean. So again, the mean here of the x bars, remember this is not the mean number of eggs, it's the mean of these x bars. We've got 1,000 samples that we took out of here. It should again be equal to 35. In other words, the distribution is a distribution of means and they're all trying to estimate this number. They better dang well be centered about that number. And what we said just a minute ago is the standard deviation or the standard error of the sampling distribution is going to be equal to 18.2 divided by the square root of 45, okay? All right, now what if we did a new sampling distribution based on our new budget because, our research budget got drained, price of eggs went way up, something happened here, the hens got hard to find, whatever the case, but this could again be the sampling distribution of x bar, but this time n is equal to 10. Well, it's going to be not as flat as our original distribution, but it's definitely going to be flatter than this one. And why? Well, because the standard deviation has changed to be larger. We're still going to be centered about 35, but now the standard deviation of our x bars is equal to 18.2 divided by the square root of 10. And so let's go ahead and calculate that number just to show that the standard deviation got bigger. So, I mean, hopefully intuitively that makes sense, but let's go ahead and do the actual number here. Again, close that bad boy off with the parenthesis there. And we see now the standard deviation of the sampling distribution of x bar, better known as the standard error of the mean, is equal to 5.7553 3, okay? So the standard deviation went up. So what does that all lead to? That was a long way of saying that the variability is greater due to the smaller sample size. So bada bing, bada boom, it's that one, okay? All right, well, hopefully that helps you with this. Definitely, if you need to, go back and do a bit more reading on chapter 4. This is not an easy read. It definitely takes a bit to understand, but once you get it, it really starts to make sense. That's why you may have noticed that there's been kind of some repeats in the reading quiz. Okay, let me know if this helps. If it doesn't, let me know that too.